short grouped?
No, I cannot see it. Can you stop sharing and share again?
Unë e shifja, vërës.
Edhe unë do ta shoh normalisht, but there is a problem that. Wait a second. Now there is something like it happens with me with my computer. So if you wait, who is sharing this? Andy or
Yes.
you stopped it already? Maybe.
What are you?
No, I cannot see. That's really bad. Okay, I cannot see it. Do the others see it? Shikoni tjerët?
Po, profesor, unë e shoh.
Okay, tani e shikoj edhe unë. Po, okay, now I can see it. Okay. If Obama can do it, we can do it too.
Can I start?
You can start, Andy.
Professor?
Yes, you can start. Yes.
Okay, our topic was about metamaterials. First, we give a definition what metamaterials are. So, metamaterials are considered as the most recent achievement in the field of unconventional materials and complex media. By definition, metamaterials are artificial engineered materials exhibiting unique or unusual features which cannot be found in natural materials, allowing this way to cross the restraint faced when using natural materials in microwave and optical components.
Can you make the full screen of your PowerPoint? You have no page number in the PowerPoint. Yesterday we mentioned it was relatively important.
Yes, that's why I left it like that, so you can see from the rest of my computer side.
No. No, let's do it full screen then.
So then we continue with the metamaterials, which are similar to natural crystal due to the fact that they both are built from periodically arranged unit cells with a side length of A. These unit cells are not made from molecules or physical atoms, but from small metallic resonators that interact with an external electromagnetic wave with a length wave lambda. And the way in which the incident light wave interacts with the so-called meta-atoms define the electromagnetic features of the instrument. These medias can then be used to enter highly unusual regions. For instance, a region where the electric permittivity and the magnetic permeability become negative at the same time, which is also the special case of metamaterials. It's an artificial thing. Then we have given the formulas of electric permittivity. So just to say a definition, electric permittivity is the ability of a material to store electrical potential energy under the influence of an electric field measured by the ratio of the capacitance of a capacitor with the materials as dielectric to its capacitance with vacuum as dielectric. Then to go to the formula, it's U0, which is equal to 1 over U0 times C squared, where U0 indicates the magnetic constant and C the speed of light. Then we have magnetic permeability. The definition of magnetic permeability is relative increase or decrease in the resultant magnetic field inside the material compared with the magnetizing field in which the given material is located. Its formula is U, which is equal to B over H. B indicates the magnetic flux density and H the magnetic field strength. Then we have the special case negative refractive index. Negative refractive index is an important characteristic in metamaterial design and fabrication. It is considered to be the factor by which the wavelength and the speed of radiation are reduced with regard to their vacuum values. In negative index metamaterials, both permittivity and permeability are negative, resulting in a negative index of refraction. Metamaterials use this feature to redirect waves. Here we also have a picture when it shows the positive refraction and negative refraction of the wave. Then we have given a Maxwell equation of the refraction, which is n squared equal to E times U, so permeability and permittivity, and also the proof that it is negative.
Can you make this full screen? Can you make the full screen the PowerPoint?
Just hold on.
No, if you click the
The backdrop should be.
poshtë fare, është një si tip kupe, si kupa aty e kalove me mouse. Jo aty. Hajde pak to your left, Ashtu në atë lartësi qendro. Ecë edhe kalo aty. Okay, that's good. Can you mund të klikosh aty hide? Perfect. Okay. You can continue.
So send down this one, and then we have the classification of metamaterials. The properties of a metamaterial are the ones that define the response of a certain system towards the presence of electromagnetic field. To describe these properties, we use two microscopic parameters such as permittivity A and permeability U of these materials. Using these parameters, we can classify the metamaterials as follows. First, we have ENG material, which is also called epsilon negative, where E, the permittivity is less than 0, and the permeability U is greater than 0. In special cases, those happens mostly to plasmas. Then we have the DPS material, which is the double positive. Here we have the ordinary effective media, and it is used the right-handed media. Here, when the permittivity and the permeability are both greater than 0, and it happens with the dielectrics. Then we have the MNG, the mu negative, when permittivity is greater than 0 and permeability less than 0. Mostly in the magnetic materials. And in the end, the DNG material, which is the so-called double negative, when both epsilon and U, the permittivity and permeability are both negative, and it's not found in nature, it's found only in artificial cases. That's why that's what the meaning of metamaterials is. This was my part, Professor.
Yes, we can continue with Luciano.
Yes, then we are going to get the applications. I don't know if Luciano is going to present from his computer or start.
He can continue. If you have the same slide, he can.
Yeah.
You can do next. You can do next in the slide. Luciano can.
Okay.
Speak.
Po profesor, po I prezantoj me kompjuterin tim.
Okay.
Professor.
Yes.
Just saying, I have also given some notes here as curiosity where it is applied mostly. For example, when silver, gold, and aluminium display the negative permittivity at the optical frequencies. Also for the permeability, I have given some notes.
Okay, that's good. But Luciano, you could have follow the presentation from the slides of Andy and you talk on the other side.
Profesor, a mund ta shikosh ekranin?
Shikoj, po.
Po slajdet.
Po.
Ti bëj full screen apo ti prezantoj kështu?
Full screen.
Okay. My part of the job was to present meta material products. First of all, we have material antennas. They are defined as class of antennas that are used meta materials as mean to enhance or boost their performance, such as radiant power. So in other words, in small conventional antennas, the signal is reflected back to a source via the most wavelength, while the material antennas have different structure which is able to store and relate energy that makes the size small and behaves as larger antenna. There is a picture of material antenna, anthropic hypernormative loaded antenna. In order to create a multi-input, multi-output systems, we use a dipole antenna that are loaded with high permeability antistropic materials. This concept is applied to decrease the thickness a great level in arrays of cellular base station. Mushroom antenna. A mushroom type antenna is an antenna that is designed with an array of many mushroom cells and is mostly used for Wi-Fi applications. The price of this antenna was $5 to $20.
Mm-hmm.
Gap capacitor loaded antenna. By definition, the gap capacitor loaded antenna is a collection of number of salted phases which antiphase and zero order resonance that is introduce a series of gap capacitors at centers of the patch and these radiant agents. Li-band radar system applications usually use a kind of antennas. WMD detectors. Metamaterials are used by the Army and Air Force to researchers to detect the presence of chemical explosives, biological agents, and contaminations. This science is also used for cargo and screening passenger. We have now in beans and soup, metamaterials have ability to easily manipulate the wavelength of sound that is way larger than the light. The naval research found a program which used the concept to make the submarine winds to enemies sonar by bending sound around it. Metamaterials are also used by the civilization systems to create soundproofing rooms with perfect acoustics. Seismic metamaterials. This kind of metamaterials are created one purpose to construct the adverse of efficient of seismic waves, non-main structures that exist or close to the Earth's surface. Metamaterials browser. The purpose of metamaterials browsers is to browse the electromagnetic radiation. They are superior to conventional observers because they are supplementary minimization, window adaptability, and increase effectiveness. In order to create high ratio electromagnetic radiation absorption, effective medium design primitivity and magnetic primitivity are necessary. Now, finally, we have a biosensor. As we know, biosensors are important tools in different fields such environmental monitoring, food safety, and disease diagnostication in the investigation of biological pneumonia. Recently, metamaterials have been embraced by researchers in biosensing technologies to detect label-free biomolecules and efficient cost. Thank you. This was our project.
Mm-hmm.
Okay,
Luciano. Luciano, I have a question. How big are the resonant structures in a metamaterial? How large?
Profesor, mund të jenë diku te 50 nanometër deri në 100.
Nanometer.
Po.
Nanometer, okay, mirë, 50 nanometer. Po në
variojnë ato, mund të jenë 50 deri në 100, ka 60 deri në 100, deri aty shkon.
Në rregull. Tjetër, in a waveguide. So you have a resonant cavity, or so you are saying it's 50 to 100 nanometer, okay? And so now keep this number in mind. And think about this. In a waveguide, which wavelength can propagate through a waveguide? So if the waveguide is 100 nanometer, what can be the size of the wavelength of the wave? You give something in order.
I don't know. I don't
When you say in
remember.
order, so if this is 100 nanometer, that is 10 to the power 2 nanometers. So what is the order of magnitude of the wavelength in this waveguide?
I can't remember it.
Okay, Andy,
Yes, Professor.
can you answer my question?
Can you just repeat it 1 second, please?
Yes. So if we have a waveguide which is composed of as big as your metamaterial structure, what is the size of the metamaterial resonant cavities?
Actually, I know that the record between them is that 1 meter is about 10 to the power 9 of the nanometer, so the wavelength must be really, really small.
But okay, so you are saying the metamaterial is in the order of nanometer, okay. But if this is the case, let's say 100 nanometers, 10 to the power 2 nanometers. But then the question is, how big can the wave that propagates through this waveguide, how large can it be?
Half of it, I think.
Half, okay. Can it be twice bigger?
Actually, it will depend also from the case in which we are, because it may be refracted from negative side or positive. Also, the angles, as I showed you to the permittivity and permeability cases in this figure.
Okay, so but can you tell me an order, like what would be the wavelength if the waveguide is 10 to the power 2 nanometers?
Uh, I think it will be 10 to the power 4, maybe?
Okay, 10 to the power 2 is a waveguide. I'm writing a couple of things down. You are saying A, and you're saying that 10 to the power 4, okay, for the wavelength. So the lambda can be 10 to the power 4, while the waveguide is 10 to the power 2. And we're talking about nanometers. So in this case, what could be the wavelength? So can you give us a number? So what is how many meters is the wavelength that can propagate through this waveguide? Can you do the calculations? Well, A is 10 to the power 2 nanometers, which is 10 to the power minus what? Andy, okay.
Minus 7 or
Say it again.
minus 7.
Which one is minus 7?
10 to the power minus 7.
Which one is 10 to the power minus 7? The wavelength.
The wavelength.
But you said the wavelength is going to be 10 to the power 4 nanometer?
Yes, but after calculation.
Okay. Now 10 to the power 4 nanometer.
Po profesor, 1 metër është e barabartë me 10 herë fuqit 9 nanometër.
Okay, pa.
But that's unknown.
Okay, then but then 10 to the power 4 nanometer is equal to what?
1 meter.
1 meter, not that much.
Yeah. No. Nuk kam të bëj këto llogaritje, po kur themi 11 fushin 9 do bëjmë rregull 3-shi pastaj.
E vërtet, po bëje.
Po do s'kam ku të shkruaj këto.
Shkruaj me çfarë letër? Все силы
I
тишины.
don't want to read about
Что это, Luciano? Because, as we mentioned yesterday in the session of the project presentation, I mean, what is essential for all of us, including you and me, is that we have to be specialists regarding the time scales, which would correspond to inverse frequencies, to length scales, which would correspond now, since we are dealing with waves and small structures, we're talking something about in the order of hundreds of nanometers to micrometers. So this you should include in detail, and we should be able to play with those.
10 to the power minus 5.
What is this? The wavelength or the
wavelength for when nanometers were
okay?
10 to the power 4.
Yes, it can be like this. That's correct. So how does this compare with the optical range, with the visible range that we can see?
It's really small.
Yes, but what is the range that we can see? The rainbow colors. From what wavelength to what wavelength are they?
It depends also from the colors, Professor.
Mm-hmm.
Because, for example, I also read that when it was blue, it was 470 nanometers. For green, 730.
That's true. Okay, so
For
it's 400 to
violet,
700 nanometers.
yes.
Mm-hmm.
For violet, for example, which is visible for us, is 420 nanometers.
So where is this 10 to the power minus 5 meters? Where is this with respect to the visible range of the wavelength?
Of 10 to the power minus 5.
Yeah.
It's like
So 400 nanometers is equal to 0.4 micrometers. 0.4 micrometers, and 700 is 0.7 micrometers. Now we are using micrometers as a reference, so you can choose another one also. But the wavelength, it's how can I say it? The wavelength is 10 to the power minus 5. It's 0.1. No, it's 10 micrometers, right? So 10 to the power minus 5 is 10 micrometers. So you are kind of, is this larger than your visible range, or can you see this 10 micrometer wavelength?
Yes, I think yes.
Okay.
It's still a bit small, but it's visible.
Okay, but then again, one final thing is that the permeability and permittivity, are they micro properties or macro properties of matter?
Macro property.
Macro. Okay, these macro properties, apparently they can become, now this is a question for everyone, but since Andy and Luciano are on the stage, we ask them first. So I wrote a question to everyone in the comment section. Can we have a look up over there? So we said that permeability and permittivity can be negative. The question for everyone is, can temperature be negative? So it looks like some properties, you might try to construct a relationship, how macro properties, whether they can be always positive or always negative. Okay. Then I think this will be all. But Andy and Luciano, I'm going to write a few comments in the section, because I had a look at the word that you have submitted. You are including references, but you might reduce the references regarding the websites. Okay.
Which website?
No, I mean, for example, I see. I mean the links. The website that you have used in the references in the Word document.
Yes.
Wait, let me think for a moment. For example, there is Nature publication. That's good. ResearchGate. metamaterial, diffraction, infrared. I'm looking at the references. Okay, and the references you have mentioned them in the paper. Okay, that's good. Okay, anyone has any question for Andy and Luciano? Okay, we can go to the next group then. Thank you, Andy. Thanks.
Professor, can I show also the poster and then leave?
Yes, you can. But you cannot leave.
No, of course. I mean,
You leave the floor.
no,
You can
yes,
show the poster.
and leave the stage.
Stella, yeah, you can.
Professor, can you see it?
Dilber gave an excellent answer, but I want you to comment on Dilber's answer. Andy, let me see. Try to pick up your. Yes, I can see it. Is this what is the size, standard size of this one?
It's the full size. I mean, I'm gonna print it in an A0.
A0. Okay, but then if it is A0, I believe the font size equal to 32 might be satisfactory. What is your font size? You can check that, and you remove the word saying project metamaterials. Delete project. Leave only metamaterials. And you can even write, yeah, we don't need to write project.
Okay.
Pika. Okay.
I will check it later, Professor. I will just.
Yeah, you can improve this, but please,
Is
you
it
might
okay?
include it. You should include equations in your PowerPoint. In this, what is this? Not PowerPoint. In the poster. Yeah. Include
Yeah, okay.
equations, at least a figure or a couple of figures. You should include those. Okay, so don't keep such a beautiful effort, including only text. Okay.
Okay, thank you.
You're welcome. Okay. Then, based on the request here, we can start with Stella.
Okay, so I'm starting the presentation.
Okay.
I think we can all see the screen.
I personally I can. I'm the last one to see it, but
Stopping and
sometimes I have issues.
presenting again.
No, I was seeing it. I was good. Sometimes when you start the class, you need. If you are the organizer of the class, sometimes you don't pick up the PowerPoint right away, but we are good.
Okay, so I'm starting with the PowerPoint, and then if we have time, I can show the poster and the word too.
That's good.
Me and Jayana chose to talk about camouflage. First, I want to start with an introduction to the project. Camouflage started to appear as a necessity in the Western civilizations. Military uniforms suffered from high losses due to high visibility of their uniform. They adopted drastic colors, and the first vestige of camouflage started to appear in the Koenig into the 1968. Also, another name of the camouflage is cryptic coloration. Studies of the physical properties of the signal and noise, in the case of coloration, the distribution of the reflected light in wavelength, time and space, are tangential to understanding how camouflage works. What matters is psychophysics, not physics. There is a massive reduction in the quantity of data between the physical signal and its encoding by a brain. This perceptual shortcut that camouflage can exploit, and three principal bottlenecks are in the eye, at the optic nerve, and finally through attention.
Okay.
Only the pattern of stimulation of the viewer's very limited number of classes of broadband photoreceptors. A common military framework for understanding defensive strategies was the survivability onion. This was a really great thing to read and explain. The survivability onion consists of 7 layers, which are there, identified, acquired, engaged, hit, penetrated, and affected. The step 1 is safest is to avoid danger in the first place through habitat choice or vigilance and moving away. If proximity to the predator cannot be avoided, then concealment through hiding or crypsis, hiding in plain sight is the next option. If the step 2 can't be avoided, then we go to the step 3. If detection is inevitable, then avoiding recognition or promoting misidentification is the next line of defense. Step 4 is, if correctly identified, then strategies to avoid attack can be employed, including pursuit deterrence signals, and more generally, advertisement of elusiveness. Step 5 is, if the predator does attack, then a startle or display can give time for escape. Through targeting, the predator's reflex protective behavior in response to unexpected stimuli. Otherwise, unpredictable or protean escape patterns can make capture difficult. The final step is when the final layers of the onion are avoidance of being killed or seriously injured. Here, deflection marks can misdirect to less important body parts. If we are required to find a relation between radiation temperature recorded by an infrared camera and several factors, we will write the following equation. Here we can see that the radiation temperature is identified into the spectral range of the IRE camera, and the variable that changes is the spectral range. Here, radiation temperature is denoted with TR. T is the specific constant of the IR camera. P object is the emitted power, I object is the spectral radiance of the object, and E object is the emissivity of the object. Through the application of an electric current, the surface may be heated in a standard manner. The uniform cooling occurs via the material's intricate nature. When the current is turned off, the radiation and connection permitted by the air-filled space in the architecture cools the material rapidly. The first experiment is done in the simple metal plate. In the first picture, we can see a low heat temperature. Meanwhile, in the second picture, we can see the opposite, the higher heat. In the conclusion, we can conclude that the special heat signatures are represented by the visualized colors. Electric current is applied to the camouflage material as the heat of the background rises, heating it up to match the background perfectly. In the next experiment, I've talked about the experiment done in the human subjects. In the figure 6, we can see a wristband in low temperature. Meanwhile, in the figure 7, we can see a wristband in high temperature. In the conclusion, we can conclude that a heat sink that could be located between the camouflage material and human skin was chosen. The tool was encapsulated in a wristband with this in place, and a comparable experiment was carried out. As can be shown, the greater the voltage, the greater the background match. Now it's time for Juliana to talk.
You can keep the slides, and Juliana can only use a microphone.
Yes, I'll do that.
And can you open your cameras when you are speaking?
Juliana. L-am bat în ducă de presă.
On fait vachement per reclama.
Та пресим që vjen një profesor,
10
pastaj
minuta.
ndërkohë mund t'ju tregoj posterin dhe Wordin.
E të presim pak, po mirë.
Okay.
Juliana, can you do something? Can it be fixed?
Ja, ajo doli, kështu që po hym prapë. Profesor, më dëgjoni tani?
Po, Juliana, dëgjoj po.
So I have to talk about optical camouflage. Optical camouflage is a hypothetical type of negative camouflage currently only in the very primitive stage of development. The idea is relatively straightforward to create the illusion of invisibility by covering an object with something that projects the scenes directly behind the object. It envelopes the wearer. It is placed in the image on the scene of the side opposite the viewer near, so that the viewer can see through the wearer. Although the optical is a term that technically refers to all forms of light, most proposed forms of optical camouflage would only provide invisibility in the visible portion of the spectrum.
So I can change slide? Okay.
What do we need for an invisibility cloak? Optical camouflage doesn't work by way of magic. It works by taking advantage of something called augmented relative technology, which adds computer-generated information to user-centered perception. The most augmented reality system requires that users look through a special view to see a real-world scene enhanced with synthesized graphics. But what we need to make a person invisible is a garment made from retroreflective material, a video camera, a computer projector, the special half-siphon mirror called the combiner. So a cloaking device. A cloaking device is a hypothetical or fictional still technology that can cause objects such as spaceships or individuals to be partially or wholly invisible to parts of the electromagnetic spectrum. A fictional cloaking device has been used as plot devices in various media for many years. The developments in scientific research show that a real-world cloaking device can obscure an object at least one wavelength of EM emissions. Scientists already use artificial materials called the metamaterials to bend light around an object. So, as we know, the camouflage is also used in the military. This is the design and evolution of a camouflage pattern of the Slovenian urban environment. The main purpose of using a camouflage pattern is to disrupt the basic shape of an object to hide or camouflage it in a specific environment. The Department of Textiles at the Faculty of Natural Science and Engineering at the University of Ljubljana, Slovenia, collaborated in the object research project known for Safety and Peace from 2006 to 2010, funded by the Slovenian Ministry of Defense. The basic goal of the research was to determine the procedure for designing a new camouflage pattern of the Slovenian urban environment and to visually analyze the chosen camouflage patterns in order to meet the visual properties, camouflage, and optical requirements. The experiment part included a selection of representative parts of the urban environment, a classification of digital images, composition of a camouflage matter. And the final camouflage pattern corresponded to all technical, formative, visual, and military requirements. Here's something different. It's camouflage in art. Artists and fashion designers have recently been creating a new form of art. It is known as camouflage art, which can be used to prevent computer vision algorithms with detecting faces. The digital art techniques combines makeup and hairstyling or other modifications such as special printing to help avoid automatic face detection. In this paper, research studied the camouflage interference and its effectiveness on several camouflage current state-of-art techniques. This tool can find the prominence of disguised features from facial images that consist of the face to be recognized and give suggestions for camouflage options or particular facial features or facial parts. Testing of this tool shows that it can effectively aid the artist or designs in creating camouflage sorting designs. The evolution of suggested camouflage applied on 40 celebrities across the 8 different face recognition shows that...
You can pause the slide. You can pause. Actually, we spent...
That's all about the camouflage. This is a video that Stella will present it.
Okay, before starting this video, I wanted to say that here with this video, I wanted to present a real example of what camouflage and anti-radar foley can do. During my research, I found prices that vary between $40 to $300 at most, based on the number of the foleys.
Have you listed these companies in the final report?
Okay, I will write them. Technically,
Because
I searched on Google, and the companies that appeared was Amazon and some Deutsch companies, 2 or 3. I don't remember the name,
Mhm.
but I saw that the application of this anti-radar folies was mostly in the Deutsch or
We're
the
mostly in what? We're mostly in what?
Deutschland, in Germany.
In Germany. Okay, in
I was
Germany.
talking in Deutsch. And
Yeah.
the main application of these anti-radar folies was in the forest.
Okay.
I'm playing the video now.
Yes. Mhm. So they're covering the threes. Okay. What do they do to these numbers? What is the principle? How do they make it?
What is the principle? How do they make it?
Yeah, how does it become invisible? Yes.
They cover the number with an anti-radar folly that covers the surface that it is applied by the infrared signals that camera captures.
Okay. What is the wavelength that they are using in the radars?
During my research, I found values that vary between 10 micrometers to at most 15 micrometers regarding the
Okay.
wavelength.
So this is the wavelength. You are saying 10 to 15, you said?
10 to 15 micrometers, but
Yeah, okay.
what I saw mostly was 10. Another thing that I saw regarding to values was the sheet resistance that were applied to the surface camouflage material. They vary between 0.6 ohm to 33 ohm based on the surface.
Okay. But then you have, what is the resolution? When a radar is picking up information, trying to detect an object, what is the spatial resolution, spatial resolution?
The spatial resolution that I was reading, you are talking regarding to the IR camera.
No, for example, with a radar, you are trying to see an object, okay? An object that has shapes or edges. What is the smallest edge that you can detect with a radar? That you are with a wavelength of 10 to 15 micrometer.
I don't remember well, but I think to 30 or 50
30 or 50 what?
micrometer.
Micrometer, okay. So you can detect the hairs of an animal. So let's say you are trying to see an animal or something. So I'm just saying hair of an animal because at 30, 40 micrometer, that's the thickness of a hair or human hair. So you can detect apparently with a radar, which could be a little difficult actually.
If we have a camera, let's say 50 megapixel, I think we can detect even the smallest thing. This is
Yes,
based
but
on the property technique.
yes, but this camera with so much megapixel, it is true because you are using optical range, but you are not using the radar wavelength. So the optical range is something between 0.4 micrometer to 0.7 micrometer. That is what human eye sees, and that's where the camera of a few megapixels is operating. But now you have moved up from 0.5 micrometer, you have gone to 10. You've multiplied it by 20 times. So the resolution, will the resolution be worse or better? What do you think, Jeriana? So you are switching from a wavelength equal to 0.5 micrometer to 15 micrometer. Is the resolution better or worse?
I don't know. Professor, I think that to capture a wavelength with greater resolution, it requires more, let's say, good camera. It requires a higher, how to say it? It requires a camera with higher megapixels.
Okay, higher
So it
megapixel.
increases the requirement.
Higher megapixels means more pixels on the detection plane, on the image plane. Okay, this is what this is the higher megapixels. So, but the spatial resolution, and how big can this megapixel be? Do we have an idea how big is a pixel? How large is a pixel? I mean, is there anyone who knows this one? You can enter this in the comment section. We can discuss
With
over there.
the exact value, I don't know, but it is too small, I think. In the
So how much is a megapixel? How many pixels does a megapixel have?
megapixel, mega is
So it has 10 to the power 3 times 10 to the power 3, so which is 10 to the power 6. Okay, so 1 megapixel is mega. It's kilo. Wait a second, kilo, mega, yeah. So that's
10
what
to the power 6.
mega is. So a million is 10 to the power 6. Fabian, you are correct. So that's what a megapixel is. Have you seen your cell phone cameras ever? Has anyone opened a cell phone and looked how large the SMOS is? The camera is. Has anyone opened a cell phone and see how big the camera is? Is it like 1 centimeter?
The
Is it
size
2
of the
centimeter?
camera.
The size of the detector of the camera, which is a very beautiful, shiny little black piece.
It is too small.
Camera is
It vary between the type
3
of the
millimeter.
camera.
It's 3 millimeter by 3 millimeters, which is small, so very small square area at the back side of the lens of the cell phone. Okay, so now if you have 3 millimeter, you divide 3 millimeter by 1000 millimeter, then you get something like 3 micrometer. This is the size of the pixel. But now regarding the resolution, the thing is that if yesterday we discussed about length scales of microscopes, and we discussed in the class that smaller the wavelength, higher the resolution. Smaller the wavelength, since it is difficult to make a smaller wavelength, exponential increase of the price you get. Okay, so if you go from 0.5 micrometer, which is the optical resolution, and you can see human hair, 40 micrometer spatial resolution. If you go 20 times larger in the wavelength, you get a 20 times worse resolution. Okay, so if you can see a human hair of 40 micrometers and multiply by 20, you get 40 times 10, 400 times 2, 800. So you get 800 micrometers, or around 1000 micrometers, which is 1 millimeter. So probably with a radar, you might have a 1 millimeter resolution, but you can check the numbers again. You can report. You can write this in your report. Okay, I want to thank you. And do you have any other question, any comment, or maybe you wanted to show the poster? We can have a look at the poster.
I heard you mention surface camouflage materials. What are they made of?
That's a good question.
As I have read, the surfaces are made from multi-layer graphene.
Graphene.
On top of an iconic liquid socket membrane and a thin bottom layer of gold between.
Okay. How do you turn on and off the camouflage? How do you make it visible and invisible?
It connects to an voltage supply.
Yes. Okay. Yes. That's what I was looking for this in the slide. Okay, you didn't put it.
I have it in the Word. That's why I was saying that.
I don't see it in the Word. Can you show it us? Can you show it to us in the Word? So you can have a cloth. Desh një xhup, dhe këtë xhupin mund ta mbulosh me një layer që është grafin, that you can buy it on. So where is this voltage? So actually, imagine you can wear something. You can put a thin layer of graphene, and what we should know is that you turn on and off by applying small voltage. You take a battery. You take the battery from the remote controller of your TV, 1.5 volts, or maybe you might need. How many volts do you need, Stella?
From 0 to 5.
That's correct. So it's not too much. 0 to 5 volts, it does not kill. You can hold the battery of a remote controller in your hand. It's safe. So 5 volts.
The maximum temperature applied was 55.
55 what?
Celsius. Yes.
Okay. Okay, but now we were looking more for the voltage, so we want to see it clear in the report that
I mentioned here that
no, the voltage, not the
the
temperature.
values.
The values, the operation, how it is applied, how you turn it on and off. So try to
I think the application is denoted here, but the values I haven't taken them.
Okay, so please add those.
Okay, I want to emphasize the picture here, which is the schematic of the material design, which I explained further previously. I'm showing the Word document now with the references in the end here. Another great thing was this experiment, but a little bit long, so I avoided him.
How much were these metamaterials that the price? How much was it?
Regarding the anti-rudder foley, they varies between $30 to $300 based on the number of the folies.
Okay, good. I'm going to write another question. Can you check the price of the? Can you check the price of the rudder itself? It's not it's not very difficult. Many companies sell.
Yeah, I was talking when I mentioned 300. I was talking about the rudder.
Oh, you're talking about the rudder. Okay.
The lowest price of a rudder was $150. The lowest one, as I saw on Amazon, and the opposite was 300 or at most $400.
Okay. Are these student lab equipment related, or are they commercial or to use by the military?
I think they are commercial because I found the same item in different sources. In Amazon, which can ship worldwide, so I think they can be used in.
Okay, let's go. Thank you very much, Donald, also for asking Stella and regarding her presentation.
Okay, the last one is poster.
Okay, can you zoom in a little more on this one?
Yes.
And if you have not printed this one, can you include equations here and the schematics which applies the voltage to turn on and off the visibility versus invisibility? Okay. Okay. Now you have included long text. It's predominantly long text, so you might cut a little shorter in some parts. Okay, include some equations. We see no equations. Maxwell's equations are perfect to include those. Mention the keyword graphene. Put the price of graphene. Companies that sell this graphene. Okay.
Okay.
Try to include these. Okay, Stella, thank you again. We can continue with the next group.
I'm stopping now.
Who wants to be next? Is there anyone else? So Sergio, Clea, Fabiani, okay. Fabiani wrote first. First come, first serve.